Welcome students, we are starting our study on continuity. Now foremost I would like to give you a few examples. Now this is a continuous function. And let me give you another example. Imagine as the function is progressing, there is a break and the function is moving on. Now this is a function which is discontinuous at a point x is equal to a. In other words, this function is not completely continuous because of the presence of this, we call it what is called as hole. Now whenever you have a hole, this falls into a special category, what is called as removable discontinuity. Now I'm not going to go into any details on removable discontinuity as of now to begin with. Of course I have dealt this as we progress in this course. So just for illustration's sake, in this particular example, this graph is not completely continuous because there is a hole present in this particular graph. So having mentioned or shown you these two illustrations, there are other illustrations also which will come handy. Now, for example, you have a graph of this fashion. This is a hole. Now this is actually a discontinuous graph, and that type of discontinuity is called as jump. In fact, we mention it as jump of discontinuity, and illustrations are also given as we move further. And there is another illustration also I wish to give you, D. Suppose you have an asymptote like this, and you have functions moving like this. Now in this case we have a function which is actually moving towards infinity on one side, and in this case it is moving towards negative infinity. So this is also a type of discontinuity. These two types are often referred to as non-removable discontinuity. Now I have also dealt about these two things. So as of now, these are simple examples of function which are discontinuous and a function which is continuous. Now coming back to the definition, when exactly is a function continuous? So we will be using this definition of continuity. Now this is also called as continuity of f of x at a point. Now the definition is as follows. Now f of x is said to be continuous at a point. Since I mentioned here, it is actually continuity at a point. At some point x is equal to a, if the limit x tending to a of f of x is equal to f of a. Now what is the meaning of this? This is nothing but the limit of the function should be equal to the value of the function. That is the requirement. Only when this is satisfied we will say that f of x is continuous at x is equal to a. Now when we talk about limit x tending to a of x, the meaning is we are looking for limit x tending to a minus of f of x, and that should be equal to limit x tending to a plus of f of x. And after these two things being equal, that should produce the value of the function. So with these points in mind, we are going to do a series of questions. Now let me just show you a graphical illustration. Say for example you have a function like this, right? And there is, say, let me just have a hole here and move up, right? So let me just take this point as x is equal to some a. Now as x is moving, or in other words, if this is x-axis, right, and this particular point is a, now as we approach towards a from the left side, we take a value which is very close to a from the left side, it lands over here, and that would be corresponding to some point, say b. So limit x tending to a minus of this function leads me to b. Now let me take a value closer to a from the right hand side, and that would also correspond to the value b. Now clearly the left hand limit and the right hand limit are equal, but f of a, so let me state that clearly limit x tending to a minus of f of x is equal to limit x tending to a plus f of x. So this is already achieved. So the limit is existing for the function, but is it equal to f of a? But let me write that, but at x is equal to a, what happens? At x is equal to a, there is a dot. You see that? There is a dot. F of a is not defined. So this would mean f of x is not continuous at x is equal to a. That is the conclusion. So we are going to look into a number of illustrations on this particular chapter. So as of now, I would stop here with this definition and I would let the problems do the talking. Students, we are given this question: f of x is equal to 1 over x times ln of 1 positive x over a divided by 1 negative x over a, with x being less than 0, and the function takes a value k if x equal to 0, and the function takes a value cos squared x negative sin squared x negative 1 over square root of x squared positive 1 followed by a negative 1 when x is greater than 0. So it is also given that f of x is continuous at x is equal to 0. We expected to find if f of x is continuous at a certain point, say x is equal to a, then f of a negative should be equal to f of a, and which in turn should be equal to f of a plus or a positive. So this condition should be true if you are claiming that f of x is continuous at x is equal to a. So this is the required condition to be satisfied. In other words, what I'm trying to say, I'm trying to say that the left hand limit is equal to the right hand limit, which in turn is equal to the functional value So in this question, it is given that f of x is continuous as x is equal to 0. So since it is already given from the question, it is clear that f of, in this case, continues at 0, so 0 minus is equal to f of 0 is equal to f of 0 plus. So this is already true. So since this is true, first step, what is step 1? We will find the limit of the function for x tending to 0 minus. So that means as x is approaching 0 from the left hand side. So that means we will have to get the limit. So this is equal to limit x tending to 0. So in this case, since it is already set to hold this condition, it is sufficient that I just extract the limit when x is tending to 0. So moving on, this is going to be, the function is defined as 1 over x times ln of 1 positive x over a divided by 1 negative x over a. Now I know that ln of a over b is equal to ln a negative ln b. Because of this, I can rewrite this as ln of 1 positive x over a negative ln of 1 negative x over a divided by x, and this entire thing is limit x tending to 0. And what is this? This is nothing but f of 0 minus. Now I can rewrite this by taking limit x tending to 0 ln of 1 positive x over a divided by x, followed by negative limit x tending to 0 ln of 1 negative x over a divided by x. Now applying limits, what do you get? X is tending to 0, so this is going to be 0, positive 1, that's going to be 1, so ln of 1, that's going to be 0, 0 divided by 0, followed by, similarly in this case you get 0 over 0 form, so which is equal to 0 by 0 form. Okay, for solving this, I'm going to show you a simple trick. Now suppose you have ln of 1 positive x divided by x, and you got limit x tending to 0. Now this is clearly 0 over 0 form, so if you were to apply the L'Hopital rule, this is going to be 1 over 1 positive x times differentiation of x is 1 divided by differentiation of this x is going to be 1, so you get 1 over 1 positive x. As x tends to 0, this is going to be giving you equal to 1. So what am I trying to tell you? If instead of x you got x over a, if you can rewrite the denominator to have x over a in such a fashion that the function does not get altered, then you can clearly conclude that limit x tending to 0 of this entire quantity will give us 1. So based on this particular simple trick. So my idea would be to rewrite this limit x tending to 0 of ln of 1 positive x over a divided by the denominator. What I'm going to do, I'm going to have x over a, and since I placed the x over a, I'm going to multiply it by a. So this is going to be the form. So clearly you can see that in place of x and x, I got x over a, x over a. So if I were to apply the limit, I would have this entire component leading to 1. So similarly, what I'm going to do, I'm going to feature this negative x over a in the denominator. So for that, let me just write limit x tending to 0 and then ln of 1 negative x over a. I need to have x over a, so with a negative sign, so I'm just going to place negative x over a. Now if I place negative here, there is already a negative sign featuring here, so I have to place positive here because this negative sign is already moved here. So in this case we got an additional a being featured, so what I wish to do is I would place that a there. So I can now follow this result. So by clubbing these two, this is going to lead me to 1. Now before I could apply the limits, I would like to write it as 1 over a limit x tending to 0 of ln of 1 positive x over a divided by x over a, and this is positive 1 over a limit x tending to 0 of ln of 1 negative x over a divided by x over a with a negative sign. So as I mentioned to you, these two things are going to give me 1 over a, positive 1 over a. So this is nothing but f of 0 minus. Now it's also given that f of 0 is equal to k, and when x is greater than 0, we have got cos squared x negative sine squared x negative 1 divided by root of x squared positive 1 negative 1. So this is what is given. So now what I'm going to do is I'm going to find the limit x tending to 0. This is actually f of 0 plus, and the function value is cos squared x negative sine squared x negative 1 divided by root of x squared positive 1 negative 1. There is a formula which states that cos squared x negative sine squared x is equal to cos 2x. So by this formula, this is going to be limit x tending to 0 of cos 2x negative 1 divided by root of x squared positive 1 negative 1. Now I'm going to rewrite cos 2x negative 1 as, I'm going to take the negative sign out. So if I were to take the negative sign out, this is going to be negative of 1 negative cos 2x divided by root of x squared positive 1 negative 1. Of course I would like to rationalize this, so this is going to be root of x squared positive 1 divided by root of x squared positive 1 and positive 1. So of course there is this limit which is tending to 0. I will apply the limits later on. Now there is a result which states that if you have something like this, limit x tending to 0 of 1 negative cos 2x, and that divided by 2x raised to the power of 2, then the output is going to be 1 over 2. You can easily verify this result. Now if I were to use this result, in fact this result will be true for anything. Say for example, limit x tending to 0 of 1 negative, say, cos 8x divided by 8x raised to the power of 2. This is also going to be equal to 1 over 2. Now let me just show this to you. Now by L'Hopital rule, of course this will be producing 0 over 0 form, but if we had to apply L'Hopital rule, this is going to be differentiation of cos 8x, that's going to be negative. Already there's a negative there, so it's going to be sine 8x. Now you have to differentiate 8x, so that's going to be 8 divided by differentiation of 8x raised to the power of 2, that's going to be 2 times of 8x times differentiation of 8x, that's going to be 8. So what you can do is you can cancel this 8 and you can cancel this 8. Now you have sine 8x divided by 8x. Now there is a result. Now suppose you are going to be applying a limit. This is going to be limit x tending to 0 of sine 8x divided by 8x. But there is a result which says that limit x tending to 0 of sine x divided by x is equal to 1. So if you had to apply this limit, this is going to give me equal to 1 over 2. So you can clearly verify that if you are getting a pattern of this fashion, the outcome is going to be equal to 1 over 2. Now why did I say all these things? Because I would like to get 2x raised to the power of 2 in the denominator. So to get that 2x raised to the power of 2, what I'm going to do is I'm going to have 2x raised to the power of 2 here, and I'm going to multiply it with 2x raised to the power of 2 here. That's what I'm going to do. Now if you are going to be multiplying these two things, so let me just use this space just to show you what exactly is happening. So this is going to be negative of, let me just place the limit x tending to 0 of 1 negative cos 2x. Now I've already divided, multiplied and divided by 2x raised to the power of 2. So you got 2x raised to the power of 2 over here. then we are multiplying and dividing by root of x squared positive 1 followed by positive 1. So that's going to be x squared positive 1 followed by a negative 1. And in the numerator I get 2x raised to the power of 2 followed by root of x squared positive 1 positive 1. So this is what I got. Now as I mentioned to you, this, if I were to, before I could apply the limits, let me simplify this. This gets cancelled, this gets cancelled, and I have root of x squared positive 1. Okay, that be there. Now this x squared and this x squared can be cancelled, leaving me with 4. So I'm going to rewrite that. So negative 4 times limit x tending to 0 of 1 negative cos 2x divided by 2x raised to the power of 2. So that's fine. Times, I'm using limit of the product is equal to product of the limits. So I can very well write it like this. Limit x tending to 0 of this quantity, root of x squared positive 1 followed by negative 1. Right? Now if I were to apply limits, this is going to, this positive 1, this is going to give me 0. So root of 1 plus root of 1, that's going to give me 2 there. So I already have a negative 4 and a 2 there. This is going to give me 1 over 2. So 2 and 2 gets cancelled, giving me negative 4. So what is all this? This is nothing but f of 0 plus. But given that, since f of 0 minus is equal to f of 0 is equal to f of 0 plus, I'm going to rewrite that as f of 0 minus, we had it as 1 over a positive 1 over a, f of 0 is k, f of 0 plus is negative 4. Now the question wants us to find what is 1 over a plus 1 over a plus 4 over k. So 1 over a plus 1 over a is negative 4. You see that? It's negative 4 positive 4 over k. My k is negative 4. Right? So substitute k. So what happens here? 4 and 4 gets cancelled. You get negative 4, negative 1. You get negative 5. So that is the solution for this question, negative 5. So that's the right place to draw this underline. So students, I hope you understood this question, and such questions are looking to be complicated, but you can simplify them and solve them in the fashion shown. Students, we are given this function, given that a comma b element of real number and b is not equal to 0. We have a function f of x to be equal to a times sine pi over 2 of x negative 1 for x less than equal to 0, and we got tan 2x negative sine 2x divided by b times x cubed for x greater than 0, and f of x is continuous at x is equal to 0. If this is the situation, we are expected to find 10 negative a times b is equal to what? So this is required, and it is given that f of x is continuous. So let me state the solution as follows. Since f of x is given to be continuous, this means f of 0 minus is equal to f of 0 is equal to f of 0 plus. This is true. Now x is less than equal to 0, that means x is less than 0, the same function value is given, and x is equal to 0, the same function value is given. So it is sufficient that we find only f of 0 minus and f of 0 plus. So foremost I will start off with f of 0 plus, which is nothing but limit x tending to 0 of tan 2x negative sine 2x divided by b times x cubed. I'm going to rewrite tan 2x as sine 2x divided by cos 2x followed by sine 2x divided by b times x cubed. Now taking cos 2x as the LCM, I would get sine 2x negative sine 2x times cos 2x divided by cos 2x times b times x cubed with limit extending to 0. I can take sine 2x out. I will get 1 negative cos 2x divided by b times x cubed. And is there anything else? There is also cos 2x, and this is limit extending to 0. What I'm going to do is I'm going to rewrite this as limit extending to 0 of sine 2x divided by cos 2x. Now I've got this 1 negative cos 2x. I would want to have a 2x raised to the power of 2. So x raised to the power of 2 would give me x squared, but I got x cubed here, so that means I need to place that x there. Of course I got a b there, so I will also add a b to it, and then this 2 squared will give me an additional 4 in the denominator, so I will try to neutralize it by placing 4 in the numerator. So this is what I've got. Now I can take 4 out, I can take b out, and then I would have limit extending to 0 of sine 2x divided by cos 2x. Of course there is a x here, so I will place the x times limit of the product. Limit of the product is product of the limits, so limit extending to 0 of 1 negative cos 2x divided by 2x raised to the power of 2. So this appears fine. So applying limits for this term, this would lead me to 1 over 2. So I can rewrite this as 4 over 2 times b limit extending to 0 of sine 2x divided by x times cos 2x. But we know that limit extending to 0 of sine x over x is equal to 1. But in this case it's 2x. So if I can place a 2 here, then things would work out in this fashion. So what I would do is I will place a 2 here and I multiply it by 2. So I'm going to rewrite this as 4 over 2 times b. There's a 2 there. I place a 2 in this fashion. So limit extending to 0 of sine 2x divided by 2x. So this is one quantity times limit extending to 0 of 1 over cos 2x. Limit of the product is equal to product of the limits. So I can apply the limit here. So this will turn out to be 1. So 4 over 2 times b times 2 times 1 times limit extending to 0 of 1 over cos 2x. If I were to apply the limits extending to 0, this one will be equal to 1. So I have a 2 getting cancelled here, giving me 4 over b. So this is what I have got. So what is this? This is nothing but f of 0 plus. So now we will find f of 0 minus. F of 0 minus is nothing but limit extending to 0 of a times sine of pi over 2 of x minus 1. Now applying limits, if I were to apply limits, this one would give me a times sine of pi over 2 of negative 1, which is nothing but negative a times sine of pi over 2, which is equal to negative a. Now since f of x is continuous at x is equal to 0, this implies f of 0 minus is equal to f of 0 is equal to f of 0 plus. Okay, so f of 0 I know. So in fact this means f of 0 minus is equal to f of 0 plus. F of 0 is negative a, f of 0 plus is 4 over b. So this is what we have got. So from here I can write negative ab is equal to 4. Okay, or ab is equal to negative 4. All these detections are possible. Hence, let me just use the space here. Hence, we are asked to find 10 negative a times b, which is equal to 10 negative, my AB value is negative 4, so I place negative 4, which is nothing but 10 positive 4, which is equal to 14. So this is the solution, and it's a good place for us to draw the red line. Students, we are given this question. The function is defined and it is given to be as x cubed over 1 negative cos 2x raised to the power of 2 times ln of 1 positive 2x times e raised to the power of negative 2x over 1 negative x times e raised to the power of negative x raised to the power of 2 for x not equal to 0. And for x equal to 0, it is given to be as alpha. Now, since the function is continuous, so let me start off the solution in this fashion. Since f is continuous at x is equal to 0, so this means f of 0 minus is equal to f of 0 is equal to f of 0 plus. Now, for 0 minus and for 0 plus, this is the term. And when x is equal to 0, this is what is given, alpha. So it is sufficient that we evaluate just for one particular component and then start the equating process. So what I'm going to do is I'm going to start off with f of x not equal to 0. So f of 0 minus is equal to limit x tending to 0 of x cubed divided by 1 negative cos 2x raised to the power of 2. Now I've got ln of a over b. Now there is a formula. Ln of a over b is equal to ln of a negative ln of b. Now if I were to use that formula, this is going to be ln of 1 positive 2 times x e raised to the power of negative 2x followed by a negative sign and ln of 1 negative x times e raised to the power of negative x raised to the power of 2. So this is what we have got. Now there is a formula which says that ln of a raised to the power of b is equal to b times ln a. Now if I were to use this formula, this is going to be limit x tending to 0. Now we know that 1 negative cos 2 theta divided by 2 is equal to sine squared theta, right? So that would mean 1 negative cos 2 theta is equal to 2 times sine squared theta. So I can replace 1 negative cos 2x as 2 times sine squared x. So this is going to be x cubed divided by 2 times sine squared x. This is raised to the power of 2. And followed by ln of 1 positive 2 times x e raised to the power of negative 2x negative 2 times ln of 1 negative x e raised to the power of negative x. So this is working out well. Now what I wish to do is I would like to use this property x tending to 0 ln of 1 positive x divided by x is equal to 1. So if we were to be expanding the terms, I would get x cubed over sine raised to the power of 4x times ln of 1 positive 2 times x e raised to the power of negative 2x negative 2 times ln of 1 negative x e raised to the power of negative x. So this is what I would have got upon expansion. Now I would like to divide this by x to the power of 4, multiply this by x to the power of 4, owing to the fact that this would lead me to 1. So if I were to do that, this is going to give me 1 over 4 times, and clearly x to the power of 4 can be cancelled here. So that is going to give me limit x tending to 0 of, there is going to be a 1 over x. Of course, as I mentioned to you, this would lead me to 1. Now I got ln of 1 positive 2 times x e raised to the power of negative 2x negative 2 times ln of 1 negative x e raised to the power of negative x. This is what I've got. Now I would like to bring the x inside, so this is going to be 1 over 4 times limit x tending to 0 ln of 1 positive 2x e raised to the power of negative 2x divided by x followed by negative 2 times ln of 1 negative x e raised to the power of negative x divided by x. Of course, I got the limits out. Now I'm going to use this fact, limit extending to 0 of ln of 1 positive x divided by x is equal to 1. So if I were to use that, this is going to be limit extending to 0 of ln of 1 positive 2 times x e raised to the power of negative 2x. I got an x, so all I need to do is to place a 2 here. If I were to place a 2 here, I will have to place a 2 here, and then I will have to have e raised to the power of negative 2x. If I were to have a e raised to the power of negative 2x, I will have to place that e raised to the power of negative 2x over here. So this is going to be negative 2 times limit x tending to 0 of ln of 1 negative x times e raised to the power of negative x. I got a x here, so that's fine. I want to have a negative sign here. So actually what I'm going to do is I'm going to place a positive sign and push in the negative sign inside, so that I can write this term in this fashion. So this is going to be negative, x is already there, so e raised to the power of negative x. If I were to place e raised to the power of negative x, I should also have a product multiple there. So this is what I've got. Now the idea is these terms are fine. So if I were to place negative, in fact what I'm going to do, I'm going to push this negative sign, and then if I were to push this negative sign, I don't want to have another negative sign there, so that will get neutralized, taking this negative down. Okay, so that is what exactly I'm doing here. Now what I'm going to next to do, I'm going to apply this property. So if I were to apply this property, this is going to be 1 over 4. Applying the limits, this is going to be, let me rewrite it down, x tending to 0 of 2 is there, I'll place the 2 there. So it's going to be ln of 1 positive 2x e raised to the power of negative 2x divided by 2x e raised to the power of negative 2x times limit x tending to 0 of e raised to the power of negative 2x positive 2 times limit extending to 0 of ln of 1 positive of negative x e raised to the power of negative x divided by negative x times e raised to the power of negative x times e raised to the power of negative x. I'm not splitting it because it's sufficient that I show that split over here, and that would be applied for this particular quantity also. So if I were to apply limits, what happens here, this is going to be 1 over 4 2 times, this is going to be equal to 1, x is tending to 0, this is going to be equal to 1, so I get a 2 there, positive. If I were to apply the limits, this entire thing is going to be 1, and x tending to 0, this is going to be 1, so 2 times 1 into 1, that's going to give me 2. So this is going to give me 1 over 4 of 4, which is equal to 1. So this is what the quantity is. But if you were to note the problem clearly states that when the functional value at x is equal to 0, f of x is equal to alpha. Now since f is continuous at x is equal to 0, this means f of 0 plus is equal to f of 0 is equal to f of 0 minus, or you can interchange it in the way in this fashion, say f of 0 minus is equal to f of 0 is equal to f of 0 plus, based on what or how you like, and it is exactly the same. And we have extracted the value for x not equal to 0, so that means this value is got, this value is got, and for x is equal to 0, this is the value. So this means the value of alpha is equal to 1. So that is what is required, and it is a good place for us to draw the red line. Students, we are given this function. We got a f being defined from R to R, and the function is given as follows: lambda times modulus of x squared negative 5x positive 6 divided by mu times of 5x negative x squared negative 6 when x is less than 2, and it is e raised to the power of tan of x negative 2 divided by x negative greatest integer of x when x is greater than 2, and it takes the value mu when x is equal to 2. Now, if f is continuous at x is equal to 2, we are expected to find lambda positive mu. What exactly is that value? So that is the requirement. So let me start the solution as follows. Now, since f is given to be continuous at x is equal to 2, this means f of 2 minus is equal to f of 2 is equal to f of 2 plus. So we will start off by finding f of 2 minus, which is equivalent to setting the limits to x going to 2 and taking the function when x is less than 2. So that's going to be lambda of, or lambda times modulus x squared negative 5x positive 6 divided by mu times of 5x negative x squared negative 6, which I can rewrite as limit x tending to 2 of lambda times modulus of x squared negative 5x positive 6. I'm going to write it as x negative 2 times x negative 3. So in this case, negative 2x, negative x, that's negative 5x, and okay, that's fine. So it's present inside the modulus. So this has to be divided by, I'm taking a negative sign out here. So negative mu times of x squared negative 5x, and this is positive 6. Now x is actually going to 2. So we need to get rid of the modulus. Now, to get rid of the modulus, what we need to do is we will have to find out what happens when x is going towards 2 from the left hand side. So you will have to pick a value that is very, very close to 2 as x is approaching 2 from the left side. So for that, we will have to obtain the limits when x is approaching 2 from the left hand side. So if you were to take a value of x which is very close to 2, say x is equal to 1.99999, what would you get? In this case, you would be getting a negative value, and similarly for the same x you will be getting a negative value if I were to take x is equal to 1.99. So the product of two negatives is going to be positive. So the quantity inside the modulus is giving you a positive sign, so thereby the outcome is going to be positive. So I can safely write it as positive sign lambda divided by negative u, right? I can do that. So this is going to be x negative 2 times x negative 3 divided by x squared negative 5x positive 6. That is also factored as x negative 2 times x negative 3. Of course, we have limit x tending to 2 from the left side. Clearly these two things can be cancelled, and that would leave us with lambda over mu with the negative sign, and this is nothing but f of 2 minus. So this is what you've got. Now when x is equal to 2, the function takes the value mu. So I can state that also f of 2 is given to be as mu. That is one particular observation. Now we have to find this value. So now f of 2 plus is nothing but limit x tending to 2 plus of e raised to the power of tan of x negative 2 divided by x negative greatest integer of x. Now whenever you have this greatest integer, you will have to take a value for x. Now if I were to draw the number line, this is 2, I am approaching x from the right side. Now if I were to take a value of x to be as 2.001, so what would be the greatest integer of x? Which would be 2, right? So I can safely write this as, so remember, whenever you have a greatest integer, you will have to assign a value for x and find out the greatest integer of x and then substitute it here. So this is going to be tan of x negative 2 divided by x negative 2, with limit x tending to 2 plus. Now what is this? What is this? As x approaches 2 plus, this is going to be 1, so the outcome is going to be. So that is a very interesting, because of the fact that we have a property. So now that we have got the value, let us connect all of them. So I'm going to state it here as, since f of 2 minus is equal to f of 2 is equal to f of 2 plus. F of 2 minus, this is negative lambda over mu, this is my mu, and this is my e, and we have to find the value. Hence lambda positive mu is equal to what? Now from here, if I were to connect these two together, I get negative lambda is equal to mu squared, and I can further substitute the value of mu. So this would mean negative lambda is equal to e raised to the power of 2. So these deductions are possible because of this equality. So this is equal to negative, I'm going to substitute the value of lambda. So this is going to be negative mu squared, because negative lambda is equal to mu squared. So lambda will be equal to negative, I'm going to write it down there. So this implies lambda is equal to negative mu squared. So I got that. So negative mu squared and positive, my mu is equal to e, so I can substitute that. So this is going to be negative e squared positive e. Now if I were to take my e out, this would give me negative e positive 1. So therefore lambda positive mu is e of negative e positive 1. So this is a beautiful result, and it is a good place for us to draw the red line. Students, this next question is interesting because all we need to do is to guess and check. Now the function is defined in such a way that f of x is 2 times sine of negative pi times x over 2 if x is less than negative 1, and it is modulus of ax squared positive x positive b when x lies between negative 1 and positive 1, and it is sine pi x when x is greater than 1. It is said that f of x is continuous on R, and we are expected to find a positive b. Now I'm going to write this following statement: since f of x is given to be continuous on R, that means the entire real line function is continuous. So let us find the values of a plus b when the function f of x is continuous at a given point. Say x is equal to negative 1. So it is given that f of x is continuous on R. So what I'm going to do is in order to find the value of a positive b, I'm going to take the function or consider the function at this particular point x is equal to negative 1. In other words, I'm considering the continuity of the function at that particular point x is equal to negative 1. So having mentioned this, let us so this would mean f of negative 1 minus is equal to f of negative 1, which is equal to f of negative 1 plus. So this is already given. Why is it already given? Because of the fact that the function is continuous on R, and we are taking the continuity of this particular f of x at a point x is equal to negative 1, and that's the reason we have got this condition. So this is satisfied. So now since this is satisfied, what I'm going to do is at x is equal to negative 1, I'm going to find out the values of this function. So let's do that. So what happens here is that we are actually having the number line. So this is going to be negative 1 this is 0 and this is positive 1. So we are looking at x which is less than negative 1. So that means we are looking at a function which is on this side. Now since f of negative 1 minus is same as f of negative 1, and which in turn is same as f of negative 1 raised to the power, in other words negative 1 plus, I can very well obtain the limit of f of x for this function at x is equal to negative 1. So for that I need to take this. That's exactly what I'm going to do. So this is going to be 2 times sine of negative pi of negative 1 divided by 2, which is equal to 2 times of sine pi over 2, which is equal to 2. So I've got this. Now because of the fact that I have got this equality, I can very well go a step further in finding out what happens when the approach is from the right side. That is exactly what I want to find that. So for that I am actually considering x which is greater than negative 1. So the function in that case is going to be this. So but the limit we are going to be looking at is x is equal to negative 1. It's the same limit. Important observation is that we are looking at a function where x is actually on the other side. So at x is equal to negative 1, in this case we will have to take the value for the function that is represented here. So this is going to be a of negative 1 squared negative 1 positive b, which is equal to a positive b negative 1. So this is what we have got. But whether you go to the value x equal to negative 1 from the left side or from the right side, they are both one and the same. So if I were to take this as 1 and take this as 2, and if I were to take say 1 prime, something of this fashion, clearly I can state that 1 is equal to 2 from 1 prime. So this would mean 2 is equal to modulus of a positive b negative 1. So I've got this. Now if you clearly observe that we have got a guess and check. Why did I say guess and check? Because we have got choices, either 1 or 2 or 3 or 4. So this is what we have to look at. Now from here we can actually find the solution. It's possible just by guess and check, but we will move on to one step further so that we can ascertain the value in precise efficiency. That's exactly what I'm going to do. Now if you can clearly see, the function also takes the value for the left side of 1 and for the right side of 1. So that's the connectivity next I'm going to do. Now when x approaches 1 from the left side, so that means the approach is from this side. So x is going to be taking values from the left side of 1. So when it takes the values from the left hand side of 1, this is the functional value that we are talking about. So what we will do is we will take the value of x to be equal to 1, and then we will substitute that value into the function. So x is equal to 1 will be substituted here. So that in turn would give me a of 1 positive 1 positive b, which is equal to a positive b positive 1. Maybe I can take this as some 3. Now the approach is going to be from the right end, from the other side of 1. So that means x is actually greater than 1. So when x is greater than 1, we got a function which is defined as sine pi x. So now we will use this function. Okay, also when x is going towards 1 from the right side, to find the value of the function for x is equal to 1. So this would give me sine of pi of 1, which is equal to sine pi, which is equal to 0. Maybe I take this as some 4. So clearly 3 and 4 are equal because of the fact that we are dealing with a function which is continuous. Now the only thing is that initially I took it as continuity at x is equal to -1. Now I am taking continuity at x is equal to +1. So because of this fact, 3 and 4 will be equal. So this means, this would mean modulus of a positive b positive 1 is equal to 0. So I can take this as some capital A and I can take this as some capital B. Now we have been given some choices. Now we will have to, because of the fact that the function is continuous on all r, the value for a plus b that we get here should agree with the value of a plus b that we have here, because in this case when I substitute a plus b, I should get a value 0. In this case when I substitute a plus b, I should get a value as 2. So what is the value? Now suppose if I take a plus b is equal, straightforward, right? From the very choices we will be able to easily ascertain what should be the value. Now of course you might say 3. Okay, if I were to put 3 here, say 3 minus 1 is 2. Okay, left is equal to right. But if I were to take the same 3 and substitute here, I won't get this. So this is out of the way. If I were to take -1 and substitute here, -1 is going to be -2, but we got a modulus sign, so that means we get a 2 here. If I were to place the same -1 added with +1, we get 0, and 0 is equal to 0. So conclusion, so this means a positive b is equal to -1. So that is a good place to draw the line, and this is the choice. I can understand that this needs some logical and rational thinking also. So this is a good problem, and we can move on to the next. Students, we are given this question. F of x is defined as a times modulus of x, pi negative x positive 1 for x less than equal to 5, and it is defined to be as b times modulus of x negative pi positive 3 for x greater than 5, and it is given that the function is continuous at x is equal to 5, and we are expected to find a negative b. So solution, I will start off like this. Since f of x is continuous at x is equal to 5, this means f of 5 from the left side is equal to f of 5, which in turn is equal to f of 5 from the right hand side. So this is going to be true. Now we will actually have to find the value of the function when x is approaching 5 from the left side, and equate it to the value of the function when x is approaching 5 from the right hand side. So that is exactly what we are going to do. So in this case, because of this, what I will do is I will start off for x less than 5. When x is less than 5, let me write that f of x is a times pi negative x positive 1. So at x is equal to 5, the function value is going to be a times pi negative 5 positive 1. So this is what I have got. Now when x is greater than 5, the function value is given to be as b times x negative pi positive 3. So I'm finding the limit here. At x is equal to 5, I would have b times of 5 negative pi positive 3. So actually these two are the limits that we have found. So probably I can state f of 5 negative, and this one I can state f of 5 positive. but because of this fact I'm going to take it as A. Okay, this is true. Because of A being true, I can easily equate 2 with 3. We can equate 2 and 3. So that means I got A modulus pi negative 5 positive 1 is equal to B times 5 negative pi positive 3. So I will have to go to the next line and complete the question. The value of pi is 3.14, but we got a negative 5. So the outcome inside the modulus is going to give me a negative value. So I should start with the negative sign and then say A times of pi negative 5 positive 1 is equal to, in this case 5 negative, the value of pi is 3.14. So the outcome is positive, so it's going to be positive B of 5 negative pi positive 3. We are expected to find what is the value of A negative B. So I am going to be pushing everything to this side. So negative A of pi negative 5 negative B of 5 negative pi is equal to 3 negative 1. What to do is I would like to have pi negative 5, so I would like to take the negative sign out. So that's going to be positive B of pi negative 5. In this case it's negative A of pi negative 5 is equal to 3 negative 1 will give me 2. I can take pi negative 5. In fact I want to take negative sign out. That's going to give me A negative B is equal to 2. So therefore A negative B is equal to 2 over negative of pi negative 5, which I can rewrite it by taking a negative sign out. If I were to take a negative sign out, this will become positive. So this is going to be 5 negative pi. So that is a good place for us to draw the red line. So that completes the solution for this question. Students, we are given this function. It is defined in the interval negative 1 over 3 and positive 1 over 3. The function is given to be as 1 over x ln of 1 positive 3x divided by 1 negative 2x for x not equal to 0 and k for x equal to 0, and it is said to be continuous. Now it is given to be continuous, and when we say continuous we are talking about this interval. We are expected to find the value of k. Now this is what I'm going to do. Since f is given to be continuous, I'm going to use this concept. This would mean the limit of the function will be equal to the value of the function. So that means limit x tending to 0 of f of x will be equal to f of 0, right? So what we will do is we will actually evaluate this. Now I'm going to use this space here. F of 0 is, when x is equal to 0, is given to be as k. Now this is going to be limit x tending to 0 of this entire function, so which is going to be 1 over x times ln of 1 positive 3x divided by 1 negative 2x, which is equal to k. So this is what we have got. Now what I'm going to do is I'm going to use ln of a over b is equal to ln a negative ln b. So if I were to use this property, I will rewrite this like this. So k is equal to limit x tending to 0, let it be like this. So this is going to be ln of 1 positive 3x negative ln of 1 positive of negative 2x. I'm going to write it like this, divided by, there is a x here, so x and x. Now there is another property, limit x tending to 0 of ln of 1 positive x divided by x is equal to 1. So to get that property, I need to have a 3x here. So I place a 3x, I multiply 3 there. I need to get a negative 2x. So I will push this negative sign here, and I will have a 2x here. This will become positive. In fact, I'm not adding the x, I'm just only placing the 2 here. So since I have placed this 2 here, I need to place this 2 here. So as x is tending to 0, this entire thing will become 1. This entire thing will become 1. So we would be left with 3 positive 2, and which in turn would imply that k is equal to 5. So this is a good place for us to draw the red line. So that is the completion of the solution for this question, students. Thank you. Students, we are given this function f of x is equal to cos of sin x, negative cos x, divided by x raised to the power of 4, is given to be continuous at each point in its domain, and f of 0 is equal to 1 over k. We are expected to find the value of k. So the solution, I'm going to start off like this. Since f of x is continuous, we will use this concept. What is the concept? The limit of the function is equal to the value of the function. So what is the meaning of this? This means limit x tending to 0 of f of x is equal to f of 0. So what is the function given? The function given is this: cos of sin x, negative cos x, divided by x to the power of 4. Now what is this? This is similar to cos a minus cos b, which is equal to 2 times. Of course, there should be a negative sign. Why there should be a negative sign? Because of the formula. A positive b divided by 2 times sine of a negative b divided by 2. If you don't want to use this negative sign, you can take it off and revert this. But I don't want to do that. I want to retain this to be the formula. So with this being said, this is equal to f of 0. We need to place that. So now what I'm going to do is I will first consider, probably I will write f of 0 over here. F of 0 is equal to, this is going to be limit x tending to 0 of negative 2 times sine of, my a is this is my a and this is my b. So it's going to be sine of sin x positive, and there is a presence of a x there. Let us place that x. This has to be divided by 2, and then you got a sine of sin x negative x divided by 2. So this is what we have got. This has to be divided by x to the power of 4. Now I'm going to use this concept, limit x tending to 0 of sin x divided by x, which we know will be equal to 1. So I have to get that. So what I'm going to do is I'm going to use this law, limit of the product. Say you got two functions here, limit x tending to 0 of f of x times g of x. Limit of the product is equal to product of the limit. I can very well do this. So by that I can now have, I'm going to take negative 2 out. So this is going to be limit x tending to 0 of, now sine of, this is actually my x, so it's going to be sine x positive x divided by 2. I need to have sine x positive x divided, this entire thing is divided by 2. This entire thing is divided by 2, right? So that's what I need to have. So I'm going to place that. Now once I place this component here, I will have to multiply it. So I need to multiply by sine x positive x divided by 2. So this is the, for the first case. Now this has to be followed by, of course there is x to the power of 4 there. So what I'm going to do is I'm just going to hold that x to the power of 4 for now. So this is multiplied with limit x tending to 0 of, for this quantity is going to be sine of sine x negative x divided by 2. So I'm going to have sine x negative x divided by 2. So that is already there. So once I place this, I will have to multiply this with the sine x quantity. So what I have to do is I will have to place that. So let me try to fuse it, because we don't have to overlap with these things. So I will try to place it over here. So this is going to be sine of x, so it has to be written like this, sine x negative x divided by 2. So that has to be there. So with that being placed, now what we have to do is we should also cater to that x to the power of 4. So I will just try to place that x to the power of 4 over here. Now if, of course, when the limit is moving, the limit will not touch this x to the power of 4 because of the formula that we have. So now what is happening here, this, when I apply limits, this entire component will be equal to 1, and this entire component will be equal to 1. Of course I can cancel the 2 that is present here, and now I can rewrite this. So this is going to be equal to limit x tending to 0 of sine of x positive x times sine of x negative x divided by x to the power of 4. So we got x to the power of 4. I'm going to write x cubed over here, and I'm going to write x over here. So this is what I have got. Now everything looks fine except for 2 here. So we need to place that 2. So it's going to be 1 over 2. And there is a negative sign. We need to cater that negative sign. So I'm going to place a negative sign there. So everything looks so much appropriate. Now there is a law, or there is a property which states that x tending to 0 of x minus sine x over x to the power of 3 will be equal to 1 over 6. So this is a property, or I should say it's a standard result. So by this, in this case we got sine x negative x over x cubed. So if I were to take a negative sign out, that's going to become, this can be rewritten as, I'm going to rewrite this as x negative sine x divided by x to the power of 3. Of course there is a negative sign, so that will make this as positive. So I've got a limit x tending to 0 of this quantity followed by limit x tending to 0 of sine x divided by x positive x over x. So this is what we have got. So this, as I mentioned to you, will lead me to 1 over 6. If this leads me to 1 over 6, I can rewrite this as 1 over 2. So this is going to be 1 over 6. That's fine. Now all I left is limit x tending to 0 of sine x over x. This is one quantity, and I have a positive one there. So this is what I have got. So if I were to apply the limits, so this is how it's going to be. So if I apply the limits, this is going to be my 1 here. So I can rewrite it like this: 1 over 2 times 1 over 6 times the limit x tending to 0 of sine x over x positive 1. This is going to give me 1. So this is going to be 1 over 2 times 1 over 6 times 1 positive 1. It's 2. So this 2 gets cancelled, giving me 1 over 6. So on the left, we've been working with k. So this would mean f of 0 is given to be as 1 over k. F of 0 is 1 over k. So we are expected to find the value of k. So I have not placed f of 0. So it's going to be 1 over k and 1 over k and 1 over k and 1 over k and 1 over k. So 1 over k, this means 1 over k is equal to 1 over 6. which means the value of k is equal to 6. So that is the end of solution for this question, students. So this is a good place to draw the red line. So students, these are some of the points we will have to remember. Now suppose we are given a function, say f of x is equal to 1 over x negative 1, and we are actually asked to find if f of x is continuous or not. So when we talk about continuity, we are in specific talking about the continuity of the function in the respective domain. So that is a very important point you will have to take into consideration. So immediately we cannot say this function is not continuous because of the fact that the function vanishes at x is equal to 1. Well, it doesn't matter. What matters is where exactly is this function continuous. So clearly f of x is continuous at all points. At all points f of x is continuous except which point? X is equal to 1. When x is equal to 1, of course we all know the function ceases to exist. So the most important aspect that we will have to look in when we talk about the continuity of a function is the respective domain. So if someone is asking you, check if the function is continuous, immediately you should ask, what is the domain? In which domain are you talking about? You follow me? So that is very important. Now this is very much pertinent to real life scenario. So suppose you are really doing well in a place, right? Say imagine this is place A. You're really doing well in this particular place. In other words, you are increasing. Now the likelihood of an person who is really doing well in place A, the moment he or she moves to place B, right, the chances are less. In other words, if you take a flourishing tree, a tree is really flourishing in one particular place, you root it out, you totally take it out from that particular soil and you put it in another place, the chances of the tree really flowering and producing fruit will be highly less likely. So that's exactly what I'm trying to tell you. So the point that we will have to understand here is whenever we talk about f of x to be continuous, we are looking for the domain. In this case f of x is continuous, in this case also f of x is continuous. The only thing is that x should not be equal to 0. So that is the point. So what are we really talking about on the other end? So we are actually talking about discontinuity. We are actually talking about discontinuous. So in this case f of x is equal to 1 over x negative 1 is discontinuous at what? At x is equal to 1. This is for the first function, and similarly f of x is equal to 1 over x is discontinuous when? At x is equal to 0. So this is a new concept we will be talking about. So continuity and discontinuity, these are interlinked. So having mentioned this, we'll move on to the next. The next important points to remember is, suppose they are given you, say, a function of this fashion, say 5 and say 7. The graph is not to scale and there is a point here. Now the question is, this is actually a point function and they are asking you, is this function continuous? Is this function continuous? What would your answer be? The point function, let me write that down. The point function is continuous, or in other words, if you're talking about many such point functions, you can say point functions are continuous. So that is the second point to remember. So point number 1 I've placed here. Point number 2 is point functions are continuous, and we'll move on. The final third point is this, point number 3. Inverse of a discontinuous function. What do you think? Can it be continuous? No, it cannot be continuous. So this is a very important point. Inverse of a discontinuous function cannot be continuous. Now, classic example, let me just use this space here. I'm going to use this space over here. So let me draw a discontinuous function. So this is x-axis, this is y-axis. Say imagine there is a discontinuity. This is a hole here, and this is a function. Now if you were to obtain the inverse, you want to obtain the inverse, you are actually performing a reflection on y is equal to x. If you were to perform the reflection, the function would be of this fashion, right? You see that this is the original function. To get the inverse, you are performing a reflection onto y is equal to x. Upon reflecting, this is how the function looks. So this is the inverse of this original function. The original function is already discontinuous, and its inverse is also discontinuous. So that's the underlying point. So the important point that we will have to settle here is inverse of a discontinuous function cannot be continuous. So that completes our lesson for today, students. Thank you. Students, we are starting our study on discontinuity, and we have been given a function f of x is equal to the greatest integer of x. We are expected to check if this function is continuous or discontinuous. Well, of course, if a function is not continuous, it is taken to be as discontinuous. But since the topic is exclusively focusing on discontinuity, I am making that particular point. So having mentioned that, what I'm going to use is, I'm going to use this particular property, limit extending to a of f of x does not exist or does not exist. So based on this, I will conclude that the function is discontinuous. Now, it is also imperative to note that we can also state that the left hand limit is not equal to the right hand limit. You can also use this particular property, because if the limit doesn't exist, definitely we can conclude that the function is discontinuous, right? So based on one of this, you can make your own judgments. So in this case, this is actually the greatest integer function. So since it is the greatest integer function, if you were to draw the graph, say 1, 2, 3 and so on, this is going to be of this particular fashion. So over here there's going to be a hole, it starts here, over here it's going to be a hole, and then similarly. So you can clearly visibly see the points of discontinuity. So this is of course the x-axis, and this is the y-axis. Now if you were to take the limits, say I want to find out the continuity at a point, say at x is equal to 1. I want to know if the function is continuous or not. So we would obviously check for f of 1 minus, and then we would check for f of 1 plus, right? So let me just start off over here in finding the value of f of 1 plus. Now what I'm going to do is I'm going to take x to be, in this case x is going towards 1 from the right hand side, right? The approach is from here. So I need to take a value of x that is very, very, very close to 1. Now if you had to take this, since f of x is equal to greatest integer of x, so the greatest integer 1.000001 will be equal to 1, right? So this is going to be my limit, my right hand limit. Now if x approaches 1 from the left hand side, I have to take a value of x which is very close to 1 from the left hand side, so it's going to be 0.99999, and f of x is going to be greatest integer of x, which is nothing but 0.999999, and that is nothing but 0. So clearly you can say or see that the left hand limit is not equal to right hand limit, so that means the limit doesn't exist. So this implies that f of x is equal to the greatest integer of x is a discontinuous function at every x element of the real line. Right, so that completes the solution for this question. Students, we are going to check if this particular given function is discontinuous or not. Now clearly the function is given to be as 1 negative x times tan pi x over 2 for x not equal to 1. So that means the function is or remains the same. Either you are going from the left hand side or from the right hand side, approaching this particular value 1, x is equal to 1, because this is the point that is being spoken of. So having mentioned that, we will find out the limit. So it is enough that we find the value of the limit as x tending to 1 of this particular function. So this would give us the left hand limit as well as the right hand limit, because if a limit exists, then clearly we can, or we would be in a position to say limit extending to 1 from the left side should be equal to limit extending to 1, which in turn should be equal to limit extending to 1 from the right hand side. So this is the situation. Because of this particular state, I am going to use limit extending to 1 of this function. So this is equal to limit extending to 1 of 1 negative x times tan of pi x over 2. Now applying the limits, this one is going to give me 1 negative 1, and this is going to give me tan of pi over 2 times 1. So this is going to be 0. Now this is going to be infinity, right? Because if I were to show you, tan pi over 2 is nothing but sine pi over 2 divided by cos pi over 2. Sine pi over 2 is 1, but cos pi over 2 is 0. So that means we got infinity on our end. So this is 0 times infinity form. Now whenever you get a form like this, this is indeterminate, but we will have to convert it into 0 over 0 form. So how are we going to convert it? So I'm placing the conversion to 0 over 0 form over here. So I'm going to write this as limit x tending to 1 of 1 negative x tan pi x over 2. I'm going to write it as cot pi x over 2. So if I were to apply limits, this is going to be 1 negative 1, and this is going to be cot pi over 2. So this is 0 over 0 form. Now if this is 0 over 0 form, we can apply L'Hopital rule. Now if you were to apply L'Hopital, what is the L'Hopital rule? It's nothing but differentiation of the numerator. So let me write that down. It's differentiating the numerator divided by differentiating the denominator. So this is going to be the L'Hopital rule. So if I were to differentiate this, I would get a negative 1. Differentiation of cot is cosecant squared x, that you got a pi x over 2. So pi x over 2 times the differentiation of pi x over 2 would give me pi over 2. So these two negative signs will become positive. So now I got 1 over pi over 2 times cosecant squared pi over 2 times x. So now I'm going to apply limits. So if I were to apply limits, this one is going to give me 1 over pi over 2 times cosecant What is cosecant x? Let me show you that. Now cosecant x is nothing but 1 over sine x. Now if x is equal to pi over 2, this is going to be 1 over 1, which is equal to 1. So this would mean cosecant squared x at x is equal to pi over 2 will give me 1. Right? So this is going to be 1. So if you were to flip it, this is going to be 2 over pi. So this is the case for the left hand limit and the right hand limit. So what is the meaning of this? This means the left hand limit and the right hand limit are one and the same, thereby limit is existing. Now, but just to look at the functional value, limit x tending to 1 of f of x. What is given? Let's go back to the question. It is given to be as pi over 2. So clearly these two don't agree. This and this, both of them, they don't agree. So this means f of x is discontinuous. Discontinuous at x is equal to 1. So that's a conclusion. So ultimately I can just say limit x tending to a of f of x exists, but it is not equal to f of a. So that is a good place to conclude. So we got another function. This is an illustration. It's given to be as x over x negative 1. Now we will have to check if the function is discontinuous. If f of x is discontinuous at x is equal to 1. So that is the requirement. Now first we will have to find if the function is defined. So this is another type of illustration where we can outrightly conclude whether the function is continuous or discontinuous without even checking for left hand limit and connecting it with the right hand limit and finding if they are equal and then proceeding further. So we don't have to do all these things. So in this case I'm just going to check if the function is defined, to check if the function is defined at x is equal to 1. So I'm going to substitute f of x is equal to 1 here. I get 1 over 1 negative 1, which is 1 over 0, which means infinity. So this means f of x is not defined at x is equal to 1. So when the function is not defined, clearly this means f of x is discontinuous at that particular point that we are looking for, at x is equal to 1 in this case. So that completes the solution for this question. Okay, so we have a question. This is the graph for this function. The first thing is we are asked to find if f of x is discontinuous at x is equal to 1. So the first line of check is check if f of x is defined at x is equal to 1. So find out the value that the function takes at x is equal to 1. So in this case the function takes the value 1. So this means f of x is defined at x is equal to 1. So that's fine. Now the second thing you will have to find out is, after this check, is to get the limits, left hand limits and right hand limits, and see if they are equal. Now let us check the left hand limit. X approaching 1 from the left side. From the graph we observe that limit x tending to 1 from the left side of the function is not equal to limit x tending to 1 from the right side of the function. So once you don't have, or once the condition fails here, clearly continuity is not there. So at x is equal to 1, we can conclude that f of x is discontinuous. So what are the important points we have to note here? Though the function is defined, but the limit test fails. The left hand limit is not equal to the right hand limit. And how did we find it? Right from the graph. Clearly you can see that as x is approaching 1 from the right hand side, the functional value is going to be 1. And as x is approaching 1 from the left hand side, as it gets closer and closer to 1, the value is going to be 0. So clearly the left hand limit and the right hand limit do not agree. So hence f of x is discontinuous at x is equal to 1. So the next point is, let's handle this. Now we need the graph, so let me use this space here. So first check is, I want to find out if f of x is defined. Okay, check if f of x is defined at x is equal to 3. So this is 3, at x is equal to 3, f of x is defined. So at x is equal to 3, f of x is equal to 3 is equal to 3. So this check is finished. So now I want to check if hand limit is equal to the right hand limit. Now as x approaches 3 from the left side, f of x, so let me just write that down, limit x tending to 3 minus of f of x. So this is on this side, and x is approaching 3 from the right side, so this is on this side. So as they move closer and closer, if you were to move closer and closer, you will be finding that the value that they meet up would be 2. So this will be the value no matter how close they go. So depending on the value that you take, you can clearly see that the left hand limit and the right hand limit will be one and the same from the graph. So as x approaches 3 from the left side and x approaches 3 from the right side, limit x tending to 3 minus of f of x is equal to limit x tending to 3 plus of f of x. So left hand limit is equal to right hand limit, but it differs from the functional value. So the conclusion is, but this is not equal to f of 3. That's the biggest issue that we have got. So let me reiterate. Though the left hand limit and the right hand limit are one and the same, but they do not agree to the functional value at x is equal to 3. So I can safely conclude, so this means f of x is discontinuous at x is equal to 3. So that is the conclusion for this question. Probably we'll wrap up with one more illustration to check if the function is discontinuous at x is equal to 5. Now at x is equal to 5, clearly you can see the line is heading towards positive infinity, and it's actually an asymptote. We are observing an asymptote here. So in this case, the function is actually heading towards positive infinity, and down here the function is heading towards negative infinity. So clearly you can see that at x is equal to 5, the function is not defined. So see from the graph, let me, probably I can use this space so that you can have a look at the graph. So from the graph, the function is not defined, right? At x is equal to 5, the function is undefined. So I can write that from the graph, at x is equal to 5, f of x is undefined. Okay, so that itself is sufficient for us to conclude that the function is discontinuous at x is equal to 5. But if you were to check the right hand limit and the left hand limit also as x tends to 5 from the left side. See, x tends to 5 from the left side. We are getting, the function is hitting positive infinity. And as x tends to 5 from the right side, from the right side, the function is hitting negative infinity. F of x is going towards infinity, and in this case f of x is going towards negative infinity. So this would mean the left hand limit of the function is not equal to the right hand limit of the function. Of course, I need not have to come to this particular point, but just to sake of consistent reaffirmation, I am just placing this point also. So clearly the function is discontinuous at x is equal to 5. So we will move on to. So now, students, we will give some important points that we will have to take into consideration. If you are given a polynomial to check for either continuity or discontinuity, then remember that polynomial functions is going to be continuous. In other words, you can use every polynomial function is continuous. Number 2, every rational function is continuous at every point where its denominator is not equal to 0. And point number 3, logarithmic functions exponential functions, trigonometric functions, inverse circular functions, and modulus functions are all going to be continuous. In their respective domains. So have that in mind. So these 3 points will give us a greater level of tools in ascertaining whether the function is continuous or the function is discontinuous. Students, now we will learn about the types of discontinuity. Now, if limit x tending to a of f of x, if this is existing, so there are actually 2 conditions that will flow from types of discontinuity. One would start with the limit being existence, and if it happens, then this would branch off to what is called as removable discontinuity. If in case, if the limit doesn't exist, so let me draw that, limit x tending to a of f of x does not exist, then that would branch off to what is called as non-removable discontinuity. So we start with finding the discontinuity, and then if limit extending to a of f of x, if it exists, then we have what is called as removable discontinuity. If it doesn't exist, we have what is called as non-removable discontinuity. Now in removable discontinuity, you got 2 further classes, and for that we got what is called as missing point discontinuity. Missing point discontinuity and isolated point discontinuity. So missing point discontinuity and isolated point discontinuity. Now in missing point discontinuity, f of a does not exist. In isolated point discontinuity, f of a exists. So these are the two things you got to keep in mind. This has got quite a branch. So you got 3 sects in this. So first sect is called the finite type. The next set is called the infinite type. And the last set, or the last branch, is called as oscillatory type. So we will have to see examples on all these things. Now, before we could proceed on to non-removable discontinuity, let me give you an illustration for missing point discontinuity. Now, I would like to use the space available over here. So this is a function. You've got x-axis and y-axis, and say a point 3, and the function is looking something of this fashion. So there is a hole here. Now clearly limit extending to 3 of f of x exists, right? So the function is discontinuous, and we have found that the limit of the function as extending to 3 is existing. So that means the control flows from here to removable discontinuity. So f of x as a removable discontinuity. Now the question is it a missing point discontinuity or an isolated point discontinuity? So we will have to make a choice. Now if f of a doesn't exist, then it is a missing point discontinuity. If f of a exists, then it is an isolated point discontinuity. So we are exactly going to picturize that by means of written documentation. So point number 1, we observe that limit extending to 3 of f of x exists. So this would mean f of x as a removable discontinuity. Now the question is it a missing point discontinuity or an isolated point discontinuity? Now if you were to find out the functional value from observation, the value of the function does not exist at x is equal to 3. You see here? So this means, I am placing the conclusion here, this means f of x as a missing point discontinuity. Okay, so you have to come all the way, you have to make the observation. This is point number 1, this is point number 2, and then state the reason and then make the conclusion. So this is for this particular function. So this is f of x. Now in case, this is scenario number 2. So in case, let me use this part. I want to use this space here. In case you have a graph like this, say x-axis and y-axis, and same point 3, and this is 4 and this is 5, and you have the function. So in this case clearly we can see that limit extending to 3 of f of x exists. Okay, and we can see that the function has a discontinuity, and it is a removable discontinuity. Now we will have to make a decision whether it is missing point discontinuity or an isolated point discontinuity. If it is a missing point discontinuity, f of a does not exist. If it is an isolated point, f of a exists. Now in this case, clearly, what do we see? Clearly, f of 3, what is f of 3? F of 3 is 5. So f of 3 is existing. So this would mean we will have to state all the things we stated in the previous problem, and then we will have to say f of x as an isolated point discontinuity. Okay, so that is the conclusion for the illustration of missing point discontinuity and isolated point discontinuity. So we'll move on to the next question. Now coming to the next branch where the limit doesn't exist. So naturally in this case we have what is called as non-removable discontinuity. In non-removable discontinuity you got three different categories: finite type, infinite type and oscillatory type. So clearly in finite type, a limit x tending to, say for example, a minus of this function is definitely not going to be equal to the limit x tending to a plus of f of x. Okay, so that means the left hand limit is not equal to right hand limit, but the only condition is the values produced by the left hand limit and the right hand limit, both of them should be finite. So when that happens, we say f of x as a non-removable discontinuity and it is of finite type. Now coming to the infinite type, either the left hand limit or the right hand limit, say negative, if it produces negative infinity, or in this case right hand limit, it produces positive infinity. It can be anything else. So I'm just taking for an illustration negative infinity, and for right hand limit positive infinity. Now if one of these produces an infinity quantity, it's not necessary that both of them should lead to infinity, but just one of them, either left hand limit or right hand limit, leads us to infinity. Then we say f of x as a non-removable discontinuity of infinite type. So that is for this branch. Now for oscillatory type, you wouldn't be able to have or zero in a fixed value. No fixed value. So the very word oscillatory type clearly conveys limit will have no fixed value. So let me reiterate. In this case, the limit will have no fixed value, and that is the reason we are saying it's oscillatory type. Students, we are expected to find the type of discontinuity the function has. So clearly you can say at x is equal to 1, what happens to this function? The function ceases to exist. So at x is equal to 1, you can say that f of x is discontinuous. And you can draw the red line. That's point number 1. Now you will have to identify what type of discontinuity the function has. So for that, I will want to, this is step 2, this is step 1. Now I will need to find out what happens as limit x tending to 1 for this function. Now in this case, clearly x negative 1 can be cancelled because of the fact that x is tending to 1. Okay, since x is tending to 1, so that means x is not equal to 1, so I am able to cancel it. That's a very important point to observe, but you cannot make the cancellation over here. So that is a very important differentiation that you will have to understand. So having mentioned that, you now have limit x tending to 1 of 9 negative x squared, and I'm going to apply limits. So I get 9 negative of 1 raised to the power of 2, which is 9 negative 1, which is equal to 8. So this means limit x tending to 1 of the function as a value, That's critical. Now, since the limit of the function exists, this means f of x has a removable discontinuity. Now, after this, you will have to find out if it is a missing point discontinuity or an isolated point discontinuity. So, step number 3, we have to find the value of the function at x is equal to 1. So what is f of x? F of x is x negative 1 times 9 negative x squared divided by x negative 1. So at x is equal to 1, what happens to the function? F of x is equal to 1 becomes undefined or ceases to exist. It doesn't have a value. So this is equal to not defined. So at x is equal to 1, the function doesn't have a value. So this means f of x has a removable missing point discontinuity, and that is a good place for us to draw the red line. Most important question that students might ask is, why do we call f of x to have a removable missing point discontinuity? Because that discontinuity or that particular point can be removed. So that's exactly what we are going to do. We can remove the discontinuity from f of x by redefining the function as follows. So how are we going to redefine the function? We are going to say f of x is equal to x negative 1 times 9 negative x squared divided by x negative 1. This is going to be the function when x is not equal to 1 and it is equal to 8. The function takes the value 8 when x is equal to 1, because that is exactly what we got, right? So this is how we get rid of the discontinuity, and that is the reason we call f of x to be a removable discontinuity. So we'll move on to the next question. So we'll go on to do the next question. We got a function. We expected to identify the discontinuity. So foremost, what we will have to do is we will have to find if the function is discontinuous. On observation, we see that at x is equal to 2, f of x is discontinuous. Now why do I say that? Because if you were to substitute x is equal to 2 over here, the function becomes, or it is undefined at x is equal to 2, and that is the reason we can clearly say that f of x is discontinuous at this particular point. So the next thing is we need to find out what type of discontinuity the function has. So for that, this is step 2. Let us find what happens when limit x tending to 2 of f of x. So this is going to be x squared negative 4 divided by x negative 2. I'm going to rewrite this as limit x tending to 2 of x negative 2 times x positive 2 divided by x negative 2. These can be cancelled, giving me limit x tending to 2 of x positive 2. Apply limits. 2 positive 2 is equal to 4. So the limit of f of x exists. So that means f of x has a removable discontinuity. Now in removable discontinuity, you have to find out if it is a missing point discontinuity or an isolated point discontinuity. So step number 3, we will have to find f of x equal to 2. We got to get this value. Now we know that f of x is x squared negative 4 divided by x negative 2. At x is equal to 2, the value f of x is equal to 2 doesn't exist, or I should say, the better way to say at x is equal to 2, the function becomes undefined, or the function is not defined. So at x is equal to 2, when the function is not defined, this means f of x as a removable missing point discontinuity. Okay, so that is the conclusion. Because of the fact that at x is equal to 2, I'm not able to get the functional value. The value of the function is not present, and once the value of the function is not present, that means the function is undefined or not defined. And since the function is not defined at this point x is equal to 2, I can clearly say f of x as a removable missing point discontinuity. So students, we have a question. We are expected to identify the discontinuity. First step is we need to find if the function is discontinuous. Now clearly at x is equal to 0, f of x is discontinuous. Why do I say that? Because if I were to substitute x is equal to 0, the function vanishes. So that's why I say that f of x is discontinuous. Now after you have obtained this is my step 1. My step 2, you will have to find the limit of this function as at this particular point. So we are looking at this point of discontinuity. So that's going to be limit x tending to 0 of sin x over x. So this is a popular result. So the limit of the function x. So this means f of x as a removable discontinuity. Now in removable discontinuity there are two different categories. One is missing point discontinuity and the other is isolated point discontinuity. So the third step is to find out the value of the function. So we need to find the value of the function f of x at x is equal to 0. So what is the value of the function? At x is equal to 0, clearly we know the function is not defined. So that means f of x is equal to 0 produces not defined. So this means f of x as a removable missing point discontinuity, right? So I hope that's a good place for us to draw the red line. Thank you, students. Students, we are given this question. Identify the discontinuity given that f of x is equal to greatest integer of x followed by a positive sign and a greatest integer of negative x. Now foremost, let us try to understand how the function looks graphically. Now if I were to take x to be element of integers, say let me just take x to be equal to 2. So if I were to substitute here, f of 2 is greatest integer of 2 followed by a positive sign and negative 2. So this is what I've got. Now the greatest integer of 2 is going to be 2 and the greatest integer of negative 2 is going to be negative 2. And when you add this, you're going to get 0. Now this is going to be repeating for all x element of integer. Say for example I am taking 4. f of 4 is going to be equal to greatest integer of 4 followed by greatest integer of negative 4. This is going to give me 4 negative 4, which is equal to 0. So for all integer, in other words, for every x element of integer, the functional value of x is always going to be 0. So suppose if you were to draw the graph, you would actually land up with like this. This would be the situation, no matter whether you take the integers on the right side or you take the integers on the left side. This is exactly what you will have the graph to be. Now, so let me just write that down. So f of x will be equal to 0 for every x element of z. Now what would be the situation when x is not an integer? X is not an element of z. So in other words, we are trying to take in a value. Say for example, in this case I started with 2. What would be the situation if I were to take x is equal to 2.1? So let me try that down. So f of 2.1 is equal to greatest integer of 2.1 positive greatest integer of negative 2.1. Now if this is 1 and this is 2 and this is 3, 2.1 is over here, right? So greatest integer of 2.1 is going to be 2. Now negative 2.1, this is negative 1, negative 2 and negative 3. Negative 2.1 is over here. So the greatest integer of negative 2.1 would be negative 3. In other words, I should write it like this, positive sign of negative 3, and then I would rewrite it as 2 negative 3, which is equal to negative 1. So this is what I'm getting. Any x which isn't an integer, then if you were to stretch the graph would be looking like this. You got a hole here, a line, and then you stretch it, you got a hole here, then you stretch it, you get a hole here, 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 you stretch it, you get a hole here. So this is how the graph will look. So if I were to write this, then this is going to be, for all the cases, this is what is going to be the outcome, negative 1. So f of x will take the value negative 1 for every x which is not an element of z. So this is to show you how this given function looks. Now clearly we can say that f of x is discontinuous at every x element of z, but this is not of much importance to us. We will have to find out the discontinuity of the function at any given point. So I'm going to check the discontinuity of f of x at a point, say x is equal to 1. So for that we need the graph. So first to check is, what is step number 1? Step number 1 is we need to find out the existence of limit as x tends to 1. So that means we need to check the existence of left hand limit and right hand limit. So for this we need to check limit extending to 1 from the left hand side of the function, and we need to check limit extending to 1 from the right side. Now in either cases, let us go back to the graph. Now x is moving towards 1 from the left side. So if you were to take a point which is very close to 1 and drop the line down, it is going to meet at a point negative 1. So this is actually negative 1, right? Because for all points which are non-integers, the outcome is going to be negative 1. That's the reason I've drawn this line. Now if you are going to approach 1 from the right hand side and take a point which is very close to 1 and drop that line, it will also meet at the point negative 1. So in either cases, either you move to 1 from the left side or you move to the number 1 from the right side, the outcome is always going to be -1, and this is also going to be -1. So let me just place -1 there. So that means the limit exists. So this would mean f of x as a removable discontinuity. Now, after finding this out, we need to find out what type of removable discontinuity it has. That's important, right? So for that, we need to check if f of x is equal to 1 exists and is defined. So let's do that. So when x is equal to 1, what exactly do we get? F of x is equal to 1. What happens when x is equal to 1? Go back to the graph and check it. When x is equal to 1, this is the point, right? So the function takes the value 0. So this would mean f of x is defined. Now, if f of x is defined, this would mean f of x as an isolated point discontinuity. So you need to come all the way to here in completing the solution for this question. So students, we are given this question, we are expected to identify the type of discontinuity. Now on observation, you can clearly see that at x is equal to 0, the function is discontinuous. Now once we find out the function to be discontinuous, we will have to find out what type of discontinuity the function has. So for that, the step 1 is to find out limit x tending to 0 of tan inverse of 1 over x. Does this exist? So for this to exist, we need to find limit x tending to 0 from the left side, tan inverse of 1 over x. We need to get this value, and we need to get limit x tending to 0 from the right side, tan inverse of 1 over x. Now if you were to apply the limits for the first quantity, this is going to be tan inverse of 1 over 0 minus. And if you are going to apply limits for this, this is tan inverse of 1 over 0 plus. Now 1 over 0. So let me just continue it over here. So this is equal to tan inverse of 1 over 0 minus. Now what is that equal to? That is going to be equal to tan inverse of negative infinity. Now what is tan inverse of negative infinity? That's going to be negative pi over 2. So this we have obtained when x approaches 0 from the left side. So this is nothing but tan inverse of 1 over x. Now similarly, this is tan inverse of 1 over 0 plus, which is tan inverse of positive infinity, which is going to be positive pi over 2. What is this? This is when x approaches 0 from the positive side. So we have got two values. This is the left hand limit, this is the right hand limit, and left hand limit is not equal to right hand limit. So we have a discontinuity, but apparently this doesn't exist because of the fact that the left hand limit is not equal to right hand limit. And that would mean f of x has a non-removable discontinuity. Now, in non-removable discontinuity, is it finite, infinite, or oscillatory? We need to make that decision. Now, clearly you see that you get negative pi over 2, you get positive pi over 2. So, since the left hand limit and right hand limit are both finite in nature, this means f of x has a non-removable discontinuity of a finite type. So that's a good place for us to draw the red lines. So this is a beautiful question. We'll move on to the next one. Students, we are given this question. We are expected to identify the discontinuity for this particular function. So clearly we can see that the function is discontinuous at x is equal to 0. We observe that f of x is discontinuous at x is equal to 0. Now the question comes whether limit x tending to 0 of modulus of sin x over x, does this exist? Now for this to exist, we need to find limit x tending to 0 plus modulus of sin x over x and limit x tending to 0 minus modulus of sin x over x. Now this is nothing but you have this 0 here. The approach is from the right side. So when the approach is from the right hand side, clearly modulus of sin x would give me sin x, and of course I got a x here, and this is nothing but limit x tending to 0 plus. Now this is a famous result. This is going to give me positive 1. Now when the approach for the second part, in this case x is approaching 0 from the left side, so clearly this one would lead me to negative 1 because of the fact that this is going to be equal to limit x tending to 0 of, there is going to be a negative sign, so that's why I'm taking the negative sign out. So it's going to be sin x over x, and that's going to give me negative 1. So clearly you can see that the limits that we have got don't exist, in other words don't agree. Now since the right hand limit is not equal to the left hand limit, this implies that f of x has a non-removable discontinuity. Right? That's fine. Now clearly also right hand limit and left hand limit are both finite. So this would mean f of x as a non-removable discontinuity of a finite type. Now I want to introduce a concept what is called as JOD. Now what is JOD? JOD stands for jump of discontinuity. Now if they ask you to find the jump of discontinuity, the formula is right hand limit minus left hand limit modulus. So in this case the right hand limit is positive 1, left hand limit is negative 1, so you get modulus of 2, which is equal to 2. Now if they ask you to calculate JOD, then this is the formula you will have to use. So JOD is also called a jump of discontinuity. So this is also an important concept which might be asked in objective type questions. Students, we are given this function. Identify the type of discontinuity when f of x is given to be as 2 raised to the power of tan x. Now clearly we can see that the function f of x is discontinuous at x is equal to pi over 2. When you substitute x is equal to pi over 2, this will hit infinity. So if you were to draw the graph, I want to show you how the graph looks. So this is going to be pi over 2, and the graph will be, let me just first draw the asymptotes. So the graph will come like this and it will move up, so it will be an asymptote. So clearly you can see that at pi over 2 the graph is hitting infinity. The graph will be moving towards infinity. Also there is the other side of the graph. Now this is on the left hand side. Now for the right hand side, if you were to draw the graph would come like this and move like this. This is a rough graph. So you will have graphs flowing like this. So if I were to stretch this, let me show you. This point is going to be pi, so there is intersection at pi, and this one would be 3 pi over 2. So I have to have an asymptote there. This is roughly the graph of tan x. Now probably if this is 0 and if you are going to be, this is an asymptote, okay, so the line doesn't touch the curve, and this would be negative pi over 2, and so on and so forth. So the graph will go to negative infinity on this side, and it is heading to positive infinity on the other side. So okay, so this is a rough graph. Now clearly let us study the existence of the limit as x tends to pi over 2 from the left side and right side. So this is the step 1. So what are we trying to do in step 1? In step 1 we will find if limit x tending to pi over 2 of f of x does exist. Okay, so for that we need to find out the left hand limit and the right hand limit. So let us find out x tending to pi over 2 from the left side. So the function is 2 raised to the power of tan x. Now from the left side is over here, right? So as you are moving from this side, from the left side, you can clearly see that the function is heading towards infinity. You see that? The function is heading towards infinity. So this is going to be 2 raised to the power of tan of pi over 2, which is nothing but, I told you, we already know that tan pi over 2, that's infinity. So 2 raised to the power of infinity, and that would give us infinity. So what is this? This is the left hand limit. Now let us study the right hand limit. So that is limit x tending to pi over 2 from the right side. So this is how the x is going towards pi over 2 from the right side. Now you can clearly see the function will be hitting or going towards negative infinity. So let me write that down. So 2 raised to the power of tan x, which is equal to 2 raised to the power of tan of pi over 2 being approached from the right hand side. Okay, so if we approach pi over 2 from the right hand side, of course in this case it's from the left hand side. So if I am approaching pi over 2 from the right hand side, then this is going to give me 2 raised to the power of negative infinity, which is nothing but 0. So clearly the left hand limit is not equal to right hand limit. So this would mean that f of x has a non-removable discontinuity. Now, once we know that f of x has a non-removable discontinuity, we need to find out what type it is, whether it's finite, infinite, or oscillatory. Now, clearly we see that one of the limits have an infinity. Since left hand limit is equal to infinity, this would mean f of x has a non-removable discontinuity of infinite type. So that's a good place to draw the red lines. So this would be the end of this solution. So this is a good problem, and it is also illustrating the non-removable discontinuity of infinite type.